Okay. Hi, Chen Liu.
Hi, Professor. Sorry, I always muted.
Are you in Purdue University or are you outside?
No, I'm actually working in California.
Oh, you're working in California.
Yeah.
Which company are you working for?
It's called like Skyworks Solutions. I'm not sure if you heard about it or not.
Skyward Solution.
Yeah.
I don't know, but it's good to have a working job these days, I suppose.
I agree. Yeah, I've heard so many people, you know.
People lose their jobs.
Yeah.
So what does the company do?
It manufactures like RF chips used in, you know, cell phones.
Oh, okay. At least it has something to do with microwave engineering and electromagnetics.
Oh, it does.
Yeah, so the materials of this course will be useful to you.
Yes, definitely.
But it probably is like a revision for you.
Yes.
Yeah, so you should be familiar with the materials. But you said you wanted to know something about layered medium. We just finished layered medium in a very simple way.
Yeah, but I mean, it's just good to review. And how would I say? Actually, I found that it's actually great to know that, you know, it's linked to, because for example, like SPP, I've heard about that, like surface plasmonic polariton.
Surface plasmon polariton. Yeah.
Yeah, it's been hot topic, but I never got to know exactly what's going on. I know it's just some, you know, nanoparticle, metal nanoparticle, and used for some wave guiding or whatever. But I didn't know that it can be like explained in such a like simple way.
Yeah, you can use the Fresnel reflection coefficient to explain it, but most people don't. They go through rather long derivations and equations.
Yeah.
That makes it harder to follow, you know, but I try to find the simplest way to explain it. So maybe we can begin. I guess you can see my screen. Yes. Okay, this lecture we'll talk about dielectric waveguides. And then we'll talk about TE polarization and TM polarization. And we pay a special note on the cutoff of a dielectric waveguide. And before I do that, I'd like to talk again on the generalized transverse resonance condition. Okay, the generalized transverse resonance condition is a rather powerful condition in the sense that you can find the guidance condition for a mode trapped in the layered medium quite easily. And the way to find that guidance condition is to assume that a wave is bouncing back and forth inside this waveguide. And then the wave is guided because of this bouncing back and forth. There must be some total internal reflection somewhat on this interface or on this interface, or it could be that these two regions are made of perfect electric conductors, or embedded somewhere behind this layered medium, you have perfect electric conductors. Then you can have perfect guidance because the energy cannot leave this guided region. It will be completely trapped inside, and you should have a guided mode if you look hard enough. So let's revisit the transverse resonance condition. We assume that the wave is guided. So if the wave is guided by bouncing back and forth, usually it will look something like this as it bounces back and forth. Okay. There would be a propagation in the z direction or the x direction. In this case, in this picture, I use y, and actually in later pictures I use z. I don't know why it comes out to be y here. It should be z. Okay, let's assume that this direction is z. Then the wave has to propagate in this manner in the z direction, and it has to propagate in this manner for all regions, region 0, region 1, region 2, because phase matching condition is required. Otherwise, the boundary condition cannot be satisfied. So as the wave bounces around, you know that the z phase, the phase in the z direction, is the same for all regions, and hence we just have to focus on tracking the transverse phase of this wave. So we assume that the phase is not changing in the z direction, or assume that they are the same, so we don't have to keep track of them. We just keep track of the phase as it propagates back and forth. Okay, so we can start with 1. In 1, let's assume that the phase of the wave is 1 at this location. And then after the wave propagates this distance, and let's assume that this is region 0, and then the wave will propagate with the transverse phase. I don't have to put the subscript 0. Okay, so by the time it reaches here, the wave would have gotten a phase gain by the time it reaches here. So this is the phase actually at this region over here. But by the time it reaches there, it is going to suffer a reflection. And because it suffers the reflection, the wave at this location is r plus tilde e to the minus j beta xt. Okay, it's going to have that phase variation plus the multiplication by the reflection coefficient r plus tilde. R plus tilde is the generalized reflection coefficient at this interface that relates to the reflected wave to the incident wave at this interface. So after one bounce here, the amplitude of the wave becomes as such. And then the wave is going to keep propagating in this direction more. Okay, by the time it reaches here, the wave is going to be the same amplitude, but it will have a phase gain of another j beta xt. So it will be e to the minus 2j beta xt by the time it gets here. Okay, and by the time the wave gets reflected one more time, over here it will suffer another generalized reflection coefficient, which is the reflection coefficient due to multiple reflection within the layered medium. So over here it will become r minus r plus tilde e to the minus 2j beta xt. Okay, but this wave has to become itself. in order for constructive interference to occur. So we come up with a condition that the wave becomes itself after it bounces around. And we have the condition that R minus tilde R plus tilde e to the minus 2j beta x t must be itself again. Okay, the original phase at the original location. And this has to be satisfied in order for constructive interference. So we want to look for constructive interference within the waveguide. And this condition is for that to occur. And this condition is also called the transverse resonance condition. Okay, and you can also get the glimpse of this transverse resonance condition by looking at the generalized reflection coefficient that we have derived before. For instance, we find that if you have a wave incident here, if it has the reflection coefficient R12 tilde, let's call this region 1, 2, 3, and we found that R12 tilde is given by R12. I can write the long form. Okay, the long form would be something like this: R12 plus R23 tilde e to the minus j 2 beta 2. Let me call this x. Okay, let me call this x direction, so as not to confuse you. So beta x, and then we can call this t, the thickness t. So that reflection coefficient will look something like this: 1 minus R12 R23 e to the minus j 2 beta 2 xt. Okay, we have seen the derivation of this generalized reflection coefficient before. Disappearing, I don't know why. And if you look at the denominator, okay, when this goes to 0, it would mean that R12 tilde has an infinite value, and only when a guided mode exists inside this layer medium can R12 tilde go to infinity. So you see that the criterion for the existence of a guided mode is R12 R23 tilde e to the minus 2j beta 2 xt. But R12 is equal to minus R21. Okay, if you were to look at the Fresnel reflection coefficient. So because of that, I can also write the right-hand side as R21, R21 tilde e to the minus 2j beta 2 xt. Okay, so you can see an inkling of the transverse resonance condition just by studying the denominator of this generalized reflection coefficient. But you can also derive this transverse resonance condition by a physical argument. Okay, are there any questions on this? And you can easily see that in order for this condition to be satisfied, you need the magnitude of the left-hand side to be the same as the magnitude of the right-hand side. So if you take the magnitude of the right-hand side, it says that this thing has to be equal to 1. This also implies, usually, unless you go to the very complicated case, that this has to be 1. Okay, when you have this to be 1, then this equation can be satisfied with the proper phase factor that you put in there. And these reflections and their coefficients can only be one when you have, for instance, total internal reflection. Another case is when you have, say, you might not have total internal reflection, but the wave comes in, you have a PEC here. There's no place for the energy to go anywhere. So you argue by energy conservation that R12 tilde for this picture must have a magnitude of 1 because of energy conservation. And hence, because of this, when you have a layered medium, either the wave bounces around by total internal reflection, or it can bounce around because of the PEC at the far end. Okay, so we can make use of this physics to look for new technology that can guide a wave in a dielectric region. There are two kind of technologies that we can use. One is actually the case of a thin film optical waveguide. It turns out that if I have a metallic surface, which is PEC, and if I coat this with the dielectric region, okay, maybe this is air, and this is epsilon r is not equal to 1, then I can have the wave bounces like this back and forth. And in the top interface, it will suffer a total internal reflection, because when it suffers a total internal reflection, it must have an evanescent wave outside. So you will have evanescent wave out there. But here is the PEC surface. It bounces around with a reflection coefficient of 1 because PEC is not penetrable. Okay, it's not penetrable, hence the reflection coefficient is always equal to 1. You can see that from the Fresnel reflection coefficient. For instance, RTE is, say I just take the 1-2 interface between two regions is mu2 beta 1z. The way we have derived it is mu1 beta 2z over mu2 beta 1z plus mu1 beta 2z. And if you let mu1 be equal to mu2, which is the case for most optical material, okay, in optics this is usually true. And then if you remember that beta 2z is beta 2 squared minus beta x squared, let's call this the x direction, okay, then beta 1z equals to beta 1 squared minus beta x squared, and beta x are the same due to phase matching. I'm just looking at the reflection coefficient at the 1-2 interface. You can see that when I have this thing be made of metal, okay, beta 2 is omega square root of mu epsilon, and epsilon for a conductive medium is mu epsilon minus j sigma over omega. Okay, you remember that the complex permittivity for a conductive medium is given to be this. So when sigma goes to infinity, it means that j beta 2 would also go to infinity. Okay, beta 2 would go to infinity when sigma goes to infinity. And when beta 2 goes to infinity, beta 2z must go to infinity. Okay, when beta 2z becomes infinity, let's assume that beta 1 is still air region. so that this is finite, this is finite, this is infinitely large, then you can see that R12 TE, it tends to -1 when sigma goes to infinity at the PEC surface. Okay, and similarly, you can show that, sorry, this is R12 TE. Similar, by the same token, you can show that R12 TM tends to 1 when sigma goes to infinity. So you can have perfect reflection at the top and the bottom interface, and the wave will be guided. And another place where you can actually see such a kind of waveguide is when you just have two metal plates. This is called a parallel plate. Waveguide. And if you have two metal plates, PEC at the top, and then PEC at the bottom. And when the wave hits the boundary, it cannot penetrate inside, so it will bounce back with perfect reflection coefficient of either +1 or -1. And the wave can bounce back and forth between these two parallel plates, and the wave can get guided. Okay, you can read either the 350X lecture note or Kong's book on this. Okay, are there any questions regarding this? If not, let's go on to dielectric waveguide or dielectric slat waveguide. And this waveguide is more interesting because it needs no metal part. It can be made out of dielectric region, which could be glass. In the case of optical fiber, the fiber is made of glass, and then you can have guidance. And guidance happens because you can pick the material such that there is total internal reflection happening at the top interface. There's total internal reflection happening at the bottom interface. Then there's no energy leaving this guided region. The wave just bounces back and forth and get guidance, okay? So it's easier said than done. A guidance condition can be written down easily, but then doing the math is a bit complicated. And we prefer to study this waveguide because it is one-dimensional. It is actually very simple. So we can teach this in a course. But the true waveguide that you have in the present world that is dielectric is the optical fiber. And this optical fiber has essentially changed our life or changed the way we communicate with each other, because you can send an optical signal on an optical fiber. Because optical signals have very high frequencies, it has very large bandwidth. The bandwidth of an optical fiber is huge. And the moment we can communicate with each other using optical fiber, we have a huge increase in the bandwidth of our communication system. Remember, the first technology came about with radio wave. The radio wave those are kilohertz, megahertz. And then after that, we developed technology for microwave. Okay, there's gigahertz. Okay, and then optical wave is maybe 1,000 terahertz. Okay, they are quite high in frequency, and hence the wave is very, very short in terms of its wavelength. Because of the impact that optical fiber has in modern life, actually Charles Kao, who invented the optical fiber, was given the Nobel Prize in 2009, Nobel Prize. okay? But the optical fiber is quite hard to study because you need Bessel functions to study optical fiber. So we would use just a dielectric slab waveguide. Okay, in the dielectric slab waveguide, you don't need Bessel function. You just need sinusoidal functions because the wave that bounces back and forth is a sinusoidal function. And we can write down the guidance condition for this waveguide using what we have learned. Okay, so the guidance condition would be 1 is equal to R10. Let's assume that the reflection coefficient at this interface is R10. And then the other reflection coefficient is R12. Then we track the transverse phase. And let's assume that the transverse phase is changing in such a manner that after the wave bounces 2 times around, the total phase that it accumulates is given to be that, okay? And it has to become itself. Whereas D, as you can see from this picture, is the thickness of the dielectric slab, okay? And as I said before, when you have total internal reflection, all this would become just 1. And this equation can be satisfied because, as you have learned before, at total internal reflection, Rij is of the form of A plus Jb over A minus Jb when total internal reflection occurs. And hence, you can easily convince yourself that when this is the case, then the magnitude of Rij must be 1 because the numerator and the denominator are just a complex conjugate of each other. There's the same complex number, but complex conjugate of each other. Okay, so when we have total internal reflections at the top and the bottom interface, then guidance is possible. Okay, and to make things simpler, we will make R12 to be the same as R10. Okay, so which means that we will say mu2 is equal to mu0, epsilon2 is equal to epsilon0 to simplify our life. And that you know what R10 is for the TE case. For the TE case, if I were to say that we're only studying the TE case here, R12 would be equal to mu, let me see, it should be mu0 beta 1x. I have a coordinate change over here because now I call this the x-axis instead of the z-axis. So this thing should now be called beta 1x and beta 0x. Okay, instead of beta 1z and beta 0z. Because of my coordinate change. This is mainly due to convention. Due to the convention that when we study waveguide, we assume that the direction of propagation of the wave is usually z. And because we have to adhere to convention, we change the definition of the Fresnel reflection coefficient by changing from z to x. Okay, before that, when we derive this Fresnel reflection coefficient, the axis vertical and perpendicular to the interface is called the z-axis. Now it's called the x-axis. Okay, so how can we solve this equation? It looks rather complicated. Okay, for the TE case, we can say that, well, R10 is equal to something that has a Guth-Hessian shift in it. Okay, that has a Guth-Hessian shift in it. And then if you look at for the face of this numerator, it will be arctangent of B over A using simple complex analysis. And then this would be minus the arctangent of B over A. Okay, and you can work this out quite easily using Fresnel reflection coefficient that we have just written down on the previous slide. Okay, that Fresnel reflection coefficient is this. And when you have total internal reflection, this beta 0x becomes an imaginary number. And this reflection coefficient would have an amplitude of 1. So I'm going to say that, well, beta 0x is going to become an imaginary number. It's going to be just this imaginary number. And if you plug in the correct numbers now to look for the goose tension shift, you'll find that this thing over here is e to the j theta te, and that phase is actually equal to e to the 2j because of the 2 times that it happens, arctangent of the ratio of the complex number, the imaginary number, to the real number. Okay, if you look at this and if you look at the previous one of this becomes a pure imaginary number because of this change. And if you look for this phase, then the phase is just that over there. And this is the phase shift. Now, of course, we have learned this to be the goose tension shift before when we study total internal reflection. Okay, so how do we solve this problem? In order for guidance to occur, we say that R10 square times e to the minus 2j beta 1x d must be equal to 1. Okay, that is the transverse resonance condition. And if you square this, okay, and take the phase of that, you will have, in order for this phase to be equal to 1, this equation to be equal to 1, it must be for the arctangent. I put a factor of 2 in because of the squaring, so that becomes that one. Okay, mu 0, beta 0, beta 1x. And let me make this in. This must be equal to 2n pi. Sorry, there should be this phase of 2 beta 1xd must be equal to 2n pi, because I can write the right hand side as e to the j 2n pi. Okay, so I match the phase, right hand side and left hand side. I should have this as my equation for guidance. In order for this equation to be satisfied, this has to be true. And this equation is not easy to solve, but it can be solved nevertheless. So what we need to do then is actually to divide this equation by 4. Okay, the trick is to divide this equation by 4. Okay, and if you do that, then this factor of 4 will go away, and you would have arctangent of this being equal to the rest divided by 4, and then you take the arctangent away by taking the tangent of the equation. Okay, and then on the other side, you have something divided by 4, so it will become n pi over 2 plus, because it divided by 4, you take this to the other side, it become beta 1x d over 2. Okay, and then because you take the arctangent from the left-hand side to the right-hand side, you have this equation over here. Can everybody follow the derivation that arrives at the bottommost equation? Okay, so it's quite simple. If you can't follow, you can actually go to the algebra and arrive at the bottom equation. So this equation is difficult to solve. It is the kind of equation that we say that is implicit. It actually is transcendental. Somebody would use that term, transcendental, and no closed form solutions. So one way to solve this equation is to use the graphical method. Okay, so graphical method allows us to solve this equation. you can also kind of intuit that you can set n to an even number and an odd number. You can get two different sets of equations to solve. For instance, if I set n to be an even number, okay, this is just pi over 2, and then maybe pi and so on, then this equation would just become a simpler equation in a sense. So when n is equal to even, the transcendental equation that I have becomes something like mu1 alpha of 0x is mu0 beta 1x tangent of beta 1x d over 2. Okay, and this thing just disappears. I'm using the fact that if you're familiar with the tangent of the theta function, if you just plot tangent as a function of theta, it looks something like this, that when theta is equal to pi over 2, it goes to infinity, and then it becomes something like this. And then this is pi over 2, this is pi, this is 3 pi over 2, and so on. So if you are at the case where n is even, you will either hit this point, or this point, or this point, and you can all replace them with the tangent. Okay, it's just a periodic function, so you don't have to write over again. However, if n is odd, what you have then is that this factor that you have here will be pi over 2. Okay, you shift the thing by pi over 2, or 3 pi over 2, or maybe 5 pi over 2, and so on. So you hit the infinity values. Okay, and then you hit the infinity value so that this equation can be written as a cotangent of something. So it would become 0x minus this, the sign flip, because actually hit the infinity at the place where it changes sign. So you have two simplified equations to solve in a sense, either when you pick n even or when you pick n odd. And this still cannot be solved easily. So what you need to do then is to find graphical methods to solving this equation. And what you find eventually is that when you pick n to be even, the guided modes will look something like this. The guided modes would be a standing wave inside the dielectric slab waveguide, because it corresponds to waves bouncing back and forth between these two interfaces. It is due to total internal reflection. The wave bounces back and forth. And because of total internal reflection, the wave is evanescent outside. Okay, and then you have odd mode, where the field profile is an odd function of x, and then you have the even mode, where the field profile is an even function of x. That detail I will not go into, but if you look at the solutions, that is how they look like. The most important thing is notice that the waves are evanescent outside. They're evanescent outside, so the wave is exponentially decaying outside. And because of that, the energy of the wave is being trapped inside the dielectric slab waveguide, and that's how guidance comes about. Okay, so the next thing that we should look at is how to solve these equations graphically. Okay, it turns out that to solve these equations graphically, I have to do some work some more. I have to convert this equation so that it is amenable to solving by the graphical method. Okay, so it turns out that since the right hand side is a cotangent as a function of beta 1x, okay, and then it's a cotangent as a function of beta 1x, it is easier to solve this equation in terms of beta 1x variable instead of some other variables, because you know that alpha 0x is actually something that comes from, you know, beta 0x becomes j alpha 0x. So you know that beta 0x square by the dispersion relationship in region 0 would be equal to beta 0 square minus beta z square. Okay, and then you know that region 1, you will have this to be true. And beta 0 is the same. It's same every region due to phase matching. And because of these two equations, you can subtract the two equations to eliminate beta z and express beta 0x as a function of, you can subtract the two equations to express alpha 0x in terms of the thing. And if you subtract the two equations, then you will have something like beta 1 square minus beta 0 square minus beta x squared. Okay, this should be beta 1x squared, sorry. If I just subtract the two equations, I will get this equation. Okay, then this should be a minus sign here. And I'm going to do this trick and then multiply this equation by d over 2. And so that what I have will look like something that this factor is the same as that factor in the thing. I'm also going to multiply this equation by d over 2. Okay. And I'm going to, of course, write my alpha 0x using this equation over here. So everything will be in terms of beta 1x. So only variable I have in my equation is beta 1x. Okay, because beta 1s cannot be changed. Beta 0 cannot be changed. Only this number can be changed. And when I plot this thing, I keep that in mind. Okay, I keep that in mind. What I have then is that I can plot the left-hand side and the right-hand side of these two equations. Okay, left-hand side and right-hand side of these two equations. And at places where the curves meet each other, those are the solutions to this highly complex dielectric waveguide problem. So what I have done here is actually to plot the left-hand side. Okay, left-hand side is actually this equation over here. And as I point out before, left-hand side, after you multiply by d over 2, is given by alpha 0x d over 2. Okay, I'm going to assume that mu1 and mu0 are the same. Okay, I'm going to assume that mu1 equals to mu0 to make things simpler. So the right-hand side is just alpha 0x d over 2. Okay, and if I write it out in gory detail, what alpha 0x is given by this equation over here. But because I multiply everything by d over 2, I bring the d over 2 inside the integrand, or not the integrand, inside the square root sign, I get d squared over 4. So the left-hand side will look something like this. So this is the left-hand side. Okay, for both of the equations. Okay. And then the right-hand side would become either this term or that term. Okay, so I will call that y1. Okay, actually I still kept my mu0 and mu1 here. Actually, they usually should just be equal to 1. So for the first equation, I will get something like this for the right-hand side. Okay, and then for the second equation, I will get something like this on the right-hand side. So I can plot y1. These are the plots of y1. They are something that looks like the tangent function, except that it's been modulated by this beta 1xd. So it still looks very much like the tangent function. Okay, and then when I plot y2, I get this expression over here, and these are the y2 plots. Okay, it has the interesting fact that when beta 1x d is equal to 0, this thing goes to infinity. But then because it's multiplied by this factor over here, this thing tends to a finite value. So y2 would look something like this. And this is another plot for y2 and so on. So the even and the odd solutions are given by these different plots. And the point where the left-hand side plot meets the right-hand side plots are the solutions of these transcendental equations. Okay, these are the graphical methods to solving this problem. But actually, these problems can be solved by a computer very easily. But graphical methods still offers you physical insight. Okay, so are there any questions on this graphical methods before we talk about the physical insight we can intuit from these plots? Okay,
Professor?
Yes?
Does that mean that there will be only TE0 and TE1 mode there? Like
Yeah, for this particular problem, for this particular plot, there are only two solutions. But the problem I have here is that this is the equation of a circle. I don't know if you can see that this is the equation of a circle.
Yes.
So if I write y3 square equal to a constant square minus x square. Okay, if I write this being x square, and this is y3 square, you can see that this is an equation of a circle. That's why when I plot the left-hand side, I get a circle. Okay, because the variable here is my x. Okay, and the vertical axis is my y. Okay, so you can change the radius of this plot, and you will have more solutions. How can I change the radius of this plot? I can change the radius by increasing the contrast between the inside and the outside. I can increase the frequency, or I can make the dielectric slab thicker. So there are three liberties that I have to increase the radius of the circle. And if the radius of the circle is bigger, you can see that I can pick up more and more solutions. Can you see that? So when frequency is higher, I will find more trapped modes. These are the trap modes inside the dielectric waveguide. Okay, and so the graphical plot and the graphical solution offers you physical insight in the sense that by increasing the contrast, increasing the frequency, increasing the size of the dielectric slab, you can find more and more trapped modes. Okay, and also there is a mode, TE0 mode, with no cutoff, which means that no matter how small you make the frequency, the smaller the frequency is, the smaller the radius of this thing. But no matter how small the radius of this circle is, there's always a solution. Whereas for the TE1 mode, if you make the radius smaller than a certain value, okay, then you wouldn't get a solution where alpha 0x is a positive number. You actually want a solution where the alpha 0x is a positive number so that the wave is evanescent. So if you find a solution where alpha 0x becomes negative, there's a no-no. That is a solution where you don't have evanescent wave outside the dielectric slab and the mode is not guided. Okay, so are there any questions on this? So we can gain some physical insight by looking at graphical solutions, even though we have computers these days which can solve these problems really rapidly. So let's use the physical insight that we have gained to see how the dispersion diagram of these guided modes would be like. We say that when the frequency is very low, okay, when the frequency is very low, what you find is that the mode has very long wavelength, and most of the energy of the mode is actually outside the waveguide. Okay, you find that alpha 0x becomes very small. Alpha 0x becomes very small means that the mode is hardly trapped. It's weakly evanescent outside. Okay, that's what happens when alpha 0x is very small. So in that case, the phase velocity of the wave resembles that of the outer medium. That is, we have a dielectric slab waveguide where this is mu1 epsilon 1, this is mu naught epsilon naught, mu naught epsilon naught. So the phase velocity as well as the group velocity, if you take the derivative of this, the beta versus the omega, that gives me the group velocity. And because the energy of the wave is outside, so you have group velocity and phase velocity approaching that of the outer medium. What happens if you increase the frequency? If you were to increase the frequency, you'll find that you find solutions where alpha 1x or alpha 0x becomes bigger and bigger. Okay, they move up this thing and become bigger and bigger. That means that the wave is more tightly trapped. Okay, its evanescence strongly outside, and the mode is strongly trapped inside the dielectric slab. And if the mode is strongly trapped inside the dielectric slab, it will approach the group and the phase velocity of the dielectric slab. That is the kind of physical insight we can gain by looking at the solution. And DM case, you can get this by using duality principle. Okay, so I will not go into detail, but physics is very similar. And these are some of the plots from Professor Kong's book. He shows that TE and TM modes are very similar. Okay, and that at cutoff, these are the cutoff frequencies of those modes. The group and phase velocities are very similar to that of the outermost medium. Whereas if you increase the frequency, the group and phase velocity approaches that of the core, the innermost region. Okay, and the plot of the guided mode will look something like this. You have odd mode and you have even modes. Okay, and all this will be written out in great detail in the lecture notes. So are there any questions before we end today's lecture? This is an important topic because the physics that we see here is the same physics as that of an optical fiber waveguide. Total internal reflection when the fiber becomes bigger, we have more track modes. And when you are close to cutoff means that the wave is weakly evanescent outside. Okay, the wave is weakly evanescent outside. Then the wave actually reaches the group velocity of the outermost medium. As you look at this plot, okay, even the TE1 mode, when you're close to cutoff, alpha 0x is 0. Alpha 0x is 0 means that we don't have any more evanescent wave outside. Then all the energy of the wave is actually in the outer region, and hence giving rise to this kind of dispersion diagrams that we see here, as well as this kind of dispersion diagrams that we see here. Okay, are there any questions?